All right, my screen is visible, right? Yes.
Yes, sir.
Okay. Let me use my stylus now. So I hope you understand this now that to see something, whether with your own eyes or you are using a machine, you have to have some excitation source that falls on the material you want to see. All right. Something has to fall there, and that is what we call as the primary probe. All right. So we call it as the primary probe, or we also call it the, when we write it, we actually write it as, 1 degree probe, right? So 1 degree probe means the primary probe. Okay. All right. Now see the situation like this. See, in no, say I'm talking about some waveform like this. Normally when we draw waveform, we draw like this. Now don't think that it is like a physically a hill, something jumping up, falling down, jumping up, falling. It's not. We normally relate this to the intensity. All right, the intensity. That means the intensity goes on increasing, then slowly it comes down to a sort of a zero or ground value, goes down to a negative value again, and this continues, and this is the way it moves. All right, it propagates. All right, I hope it is not very difficult for you to understand, but if you find it difficult, you can always ask me. Okay, that means light is coming to us from the sun. Light is coming to us, right? Taking maybe millions of years to reach us, but it is coming to us. All right, say not millions, maybe thousands of years, but it is propagating. That means light is moving. All right, and as it moves, and this when light is moving, we are actually talking about some physical particles. All right, so it is a collection of some physical particles that move, and these physical particles we call as, or we refer to as, in physics we say this is as phonon. All right, PHONON. All right, so it's all these phonons. So now when we're talking about this intensity, this is related to one phonon. All right, and it has billions of phonons in it, and each phonon will have an increase in intensity. All right, decrease in intensity, increase in intensity, and it goes on like this as it propagates. All right, and we say that this distance from the particular intensity to the same intensity in the next cycle, this distance is what is called as a wavelength, and we refer that or use the symbol lambda for it. That's a wavelength. All right, and it's a physical value of distance. Now in order to see something, we should have this is suppose the primary probe falling on something you want to see. All right, now in order to see that or visualize it, we need to have one intensity peak, at least one intensity peak of the phonon, at least when the light passes or grazes through the material or passes or falls on the material. All right, that means the phonon should have at least one intensity peak. If it is more, it's better, right? But at least one, otherwise we will not be able to visualize it, which means that this intensity peak comes in within one wavelength. All right, now I'm drawing from zero, doesn't mean that I can draw from somewhere else also, somewhere here also. If I draw it from here, it will be up to here, right? That is one wavelength. So you here see here at least one intensity peak is here. All right, so that means within one wavelength we will have at least, we will have one intensity peak, one in 10. Very difficult to write with a stylus. I don't know how you guys do it. In one intensity peak. All right, and we need at least one intensity peak to see something. That means the size that we see is governed by the wavelength of the light. Okay, that means if I want to see something which is suppose like suppose like 1 micrometer in size, all right, that means I have suppose something and this is 1 micrometer. Now to see this, the primary probe that is coming in, the wavelength has to be less than 1 micrometer, otherwise we won't get that one intensity peak. You understand? Because if it is more, that means the intensity of light falling. Suppose the wavelength is more, suppose it is 10 micrometers, then the possibility, because we see in one wavelength we have one intensity peak. That means in 10 micrometers there will be one intensity peak only. So there's no, you cannot guarantee that since this particle is 1 micrometer, that is 1/10 of the distance traveled by that light during one intensity peak. You cannot guarantee that that same intensity peak will be there when light falls on this one, because the wavelength is large. But if the wavelength is less than 1 micrometer, you can confidently say that at least one intensity peak will be there, at least. But if it's even smaller, like say 100 nanometer, then there will be many intensity peaks. So you'll nicely see this. You understand? That means the wavelength of light or any form of excitation falling on a particle, in order to see that, the wavelength has to be comparable to the size. That means you want to see something in the range of 100 nanometers, then the wavelength should be in the range of 100 nanometers or less. Otherwise, you won't see it. And that's precisely why we cannot see nanoparticles which are 20 nanometers using visible light, which starts from 400 nanometers. You understand? That's why we cannot use visible light as a primary probe for looking at things which are less than 400 nanometers. Got my point? Is it clear to everybody? When I'm asking that, I mean that if somebody, for somebody this is not clear, you ask me and say that this is not clear. Hmm? So expecting it is clear. Are you guys there or not? Somebody?
Yes, sir. Yes, sir.
This
We are
is
there.
clear, right?
Very
Okay, okay, good. So that's why when we are using or when we want to see an enlarged form of a nanomaterial, we cannot use visible light, and that's why our optical microscopes that we talk about cannot be used, because optical microscopes, they use lenses, right? Optical microscopes, they use lenses. No, I will definitely show you in one slide sometime and how an optical microscope works. But you know, this is all about lenses, all right? So they use, you know, lenses like this. So if I have a simple convex lens like this, and this is suppose the axis of the convex lens, and if I have an object here, all right, then light passing from here, okay, get reflected, and one will go through the center, and we see an image here of this particular thing, all right? So if this is like this, then here it is an inverted image, and it may be larger, right? A typical magnifying glass is a simple example. This is a magnifying glass, and you see the image slightly larger. Okay, that is magnification. So here, whatever light is going here, all right, there's a primary probe, all right, light falling on it has to fall on it, otherwise you won't see it, and all these light coming out are the secondary probes. So primary probes we write as 1 degree probes, secondary probes we write as 2 degree probes, okay. So typically for optical microscopes, since we see with our own eyes, okay, because this finally goes to our eyes, okay, we look through the lens and finally it actually goes to our eyes somewhere. All right, so our eye is the detector, all right. So since our eye can only see between 400 to 700 nanometer, it's no point in sending something else to our eyes, right? So the same thing. When we are talking about 20 nanometer, 10 nanometer, 5 nanometer, then whatever is the primary source has to have a wavelength in that size range. So what is that? Normally, what we can actually use are only X-rays. I know you have heard about X-rays. Maybe we need to explain to you, but I think you people should be knowing because this is. But for pharmacy, I don't know. But these are mostly used for medical diagnostics, right? X-rays. Why I will tell you later. But X-rays typically have about somewhere around maybe 5 nanometer wavelength. Okay, so falls in the range that we want to look at when we're talking about nanomaterials or electron beams, because electron beams, okay, electron we all know is a physical particle, right? It is not a wave actually. But it's a physical particle. But you know, if you remember your basic physics that you studied from maybe class 10 or class 11, 12, we know that everything that exists has both material property as well as wave property, right? Now, what is observed or gets reflected depends a lot on the material. Even the art, it's a huge ball, right? It's a huge sphere. So art also has both, right? So it has mass, all right, but it also has a wave property, but its mass is so big because if you remember the Heisenberg's uncertainty principle that you studied, I don't have to tell you that, but if necessary, you Google it and find it again. The Heisenberg's uncertainty principle, it says that we cannot detect the position as well as the momentum or of a particle at the same time confidently, okay, because these are interrelated and every particle has both momentum as well as the wave nature, okay. That means it is moving actually. So the thing is, think about the art, it's so huge, all right. So its momentum can be very precisely measured, all right. The mass into velocity, all right, it can be very precisely measured, okay. So but then its wave nature is not observable because ultimately this is a constant, all right. So if something is becoming bigger, the other part is becoming smaller. So this wave nature is more prominent in small sized particles, right? Because the momentum becomes less now. So you have more part because the multiple is a constant. So the momentum becomes less. The wave portion, So it's a duality theorem. So the wave part becomes more prominent. And that's why these electron beams, they are so small. Electrons are so small that their wave nature is prominent, right? That means they move around, they travel, and that is the same thing. The energy, okay, because for light we are talking about intensity. For electrons, since it's a particle, okay, physically present particle, we talk about its energy, right? So here it's the same thing. The electron is actually moving around, and its energy is moving around or going up and down like this, the same way as the wave. All right, so any other wave. So for electrons also the wave nature is prominent, and that's why we can also use electron beams as a probe for imaging, right? So seeing, right? And electron beams also typically can be from about 2.5 to about 5 nanometers in wavelength, okay. So that's just perfect for us. So think about it. For observing nanomaterials, which are very, very small, we can think about X-rays or electron beams as the primary probe. All right. Now, think about it again. The wavelength at which you are striking a sample as the primary probe, the secondary probe will also be of similar range. You cannot expect that you are you know, you are exciting with a 5 nanometer wavelength probe, and you're expecting that 400 nanometer signals will be coming out from it. It doesn't happen. That's why if you are using a primary probe which you cannot see this, right? 5 nanometer you cannot see because you cannot see less than 400 nanometers. That's the problem with our eyes, right? Our eyes can only resolve things that are within the range of 400 to 700 nanometers. So if I'm exciting with a much smaller wavelength, how can I see it? I cannot see it. That's why, honestly speaking, you actually do not see nanomaterials. I can show you a lot of pictures of nanomaterials, okay? But those are pictures. You understand? It's not your eyes seeing it. That means your eye as a detector is incapable. So we use different detectors and then we translate that into an image in the computer, okay, and then we see it because the image that is translated in the computer, we are seeing it from a different perspective. That means that one we are again seeing it because of excitation of the screen with photons that we can see, right? So once it is into an image, now we can see it, okay. X-ray sheets, okay, if you see those X-ray plates, right, have you seen those X-ray plates? Those you can see because that is already translated into image and recorded on a paper or some form of a medium, and you are using a different excitation source now to look at the image. So you are not actually seeing the real thing, you are just seeing an image, right? So same thing here for nanomaterials. You don't see the real nanomaterials with your eyes because eyes cannot do that, but you are seeing photographs or some images that are generated picking up those signals which are in the size range of the nanomaterials, right? And then it is translated into an image and we see it, okay? So that is why, to understand properly these you know, excitation probes, let's look at this small comparison that I had put in. These are different types of probes, okay? So you can have visible light as a probe. So I already discussed visible light can be only used for optical microscopy, okay? That is the using all those lenses and everything, and there we directly see. In an optical microscope you put your eye and see, right? You are not taking a picture. You can take a picture, of course, but you can see with your eyes also. So you put your eyes on the lens and you see it physically because all those secondary probes that are coming out from your sample, they're in the range that your eye can perceive. So all those photons, they're coming in at wavelengths of 400 to 700 nanometers, and you can see. All right, so for optical microscope, the primary probes are photons and the secondary probes are also photons. Okay. Now talk about X-rays as the probes. So X-rays typically are used for these two different techniques. One is called X-ray diffraction. Okay, in short, it's actually written as XRD, and X-ray photoelectron spectroscopy. Okay, it's called XPS. Now, spectroscopy, please don't mind, I'm having a cup of tea also together when I was talking to you guys. That's okay. You guys also pull in some coffee or something when you come to my class, okay? I don't want you falling asleep. Uh, that's very typical in the West and everywhere, you know. Teachers also come to class with coffee, and students also come to class with some form of a drink in their hand. Very casual, but that's okay as long as you understand. So these techniques, if I get time, I will explain in details. So X-ray diffraction is again a form of spectroscopy. Now, what is spectroscopy? So spectroscopy and microscopy are different, okay? In microscopy, you have an image that you can see, a picture, a photograph. That's in microscopy. When you talk about spectroscopy, you have a series of data of certain variations of a particular parameter. So spectroscopy will always give you a plot, a graph. Microscopy will give you an image. Spectroscopy will give you a graph, where will be a lot of information that you can pull out from those graphs. Okay, so that's again about X-ray photoelectron spectroscopy, where actually we are using electrons in the frequency in the wavelength range of we can say wavelength range or frequency range. You know they are interconnected, right? So let me just use the thing again. So frequency is the reciprocal of the wavelength. Okay, so it's c by lambda, right? So they are interrelated, obviously, because frequency talks about the number of repetitions, right? And normally when we say frequency, we talk about in its unit is hertz. We write as Hz. It is Hertz, hertz, right? And this is of course in nanometers, right? This is of course in nanometer. And c is what? The velocity of light. Is the velocity of light in vacuum. It's the velocity of light in vacuum, right? You know the value, anybody? It's 3 into 10 to the power of 8 meter per second. All right. So if it is 3 into 10 to the power of 8 meter per second, if you want to convert it to nanometer, because this is in nanometer, so 1 meter is 10 to the power of minus 9 meter. So it will be 3 into 10 to the power of 8 into 10 to the power of minus 9 nanometer per, right, per second. So this nanometer per second. So it will be 3 into 10 to the power of minus 1 nanometer per second. So if you plug this value in, okay, so you'll see here, forget about the value, but if the unit now I write here as nanometer per second, for C, let me write in nanometer per second. All right, then nanometer cancels out. So what is the unit for frequency now? Whatever remains, it remains is 1 by s, that is seconds. So frequency is per second. So hertz means number of repetitions per second. That means number of repetition means how many times you are going through the same intensity point in 1 second. All right, that is what is 1 hertz. So if it is repeating 5 times, you will say it is 5 hertz. The frequency is 5 hertz. If it is repeating 1000 times, you will say the frequency is 1 kilohertz or 1000 hertz. If it is repeating 1 million times, you are saying the frequency is 1 megahertz. All right. If it is going 10 to the power 9 times, you say it is 1 gigahertz. All right. So that is how we talk about or relate frequency with wavelength. So going back here, so now we're talking about X-rays that can be used as a primary probe. That means we can shine X-rays on a material and we can get some amount of information coming out. All right. So we can translate it to an image, like you see in your medical. We do the X-ray if our bones are broken or something. We use X-rays to take an image because our bones, they absorb X-rays. So the other part passes, bones absorb, and we can relate that into an image. Okay. And normally you've seen it is a two-dimensional image rather than a three-dimensional image. Okay. And we can use it as a spectroscopy. That means we can gather information. All right. So we are trying an intensity plot. That means whatever signal is coming out after we shine it X-ray, we can have an intensity plot of that. We can grade our material and say, okay, from here, this frequency is coming out from there, that frequency is coming out from there, another frequency is coming out. Okay. Because X-rays, as you know, they are characteristics of a material. Okay. That means very, very unique. Every material will have a different form of X-ray. Because all these X-rays that are coming out, do you know why they are called X-rays? Do you know who discovered X-ray? Anybody? Someone? If you know, tell me. Who discovered X-rays? Come on, guys. You don't know. Okay, it was by a scientist called Röntgen. And do you know why he called it X-ray? Because when he first detected these signals, he did not know where it came from. When something is unknown in mathematics, we consider it as normally as X, right? So, and then we do the calculation and find out the value of X. But initially, if it is unknown, we use it as X. That's why precisely why he called it as X-rays. Okay, because he was not at that time he didn't know the source. So X-rays are generated by electrons moving inside the atom, okay, from one orbital to another. So they, during the process, if they jump from an orbital with higher energy to an orbital with lower energy, they release some amount of, you can say, energy. They need some, because it goes from higher to a lower, right? So they release the excess amount of energy, and this is unique for every material. That means if I talk about the X-ray coming from, say, suppose gold, will be different from the X-ray coming from carbon. Will be different from the X-ray coming from, say xenon. So every element will give out a different frequency of the X-rays, because these energy variations are unique to every element. And that's why we call them X-rays as characteristic X-rays, because they refer to the characteristics of the material, right? That means once we see an X-ray coming out, if we can measure the frequency, we automatically know, oh, this frequency matches with gold. So this X-ray is coming from gold directly. It's very, very particular. So the moment we can know the frequency, we immediately know from which element it is coming. That's why if you sign X-rays and you can pick up those signals coming out, and you can actually break it up into those individual components, then you can tell what are the elements present in the material you are looking at. Okay, so you understand that? That means if I have a sample, I don't know what is the material, I generate the X-rays from there, and immediately from standard tables, I can immediately say, okay, this material has copper, this material has, zinc, and this material has maybe some amount of carbon. You can directly tell from the X-rays, because the moment the extra frequency, there's no other element can give the same frequency. All right. That's why we can use X-rays for what we call as elemental analysis. So if you have a sample and you don't know what are there, you can check. If you have a sample where you have tried to understand how the material variation is happening, that means you make a thin film, you deposit something, and you try to see if it is properly deposited or not. You simply scan the surface with X-rays. Okay, and they will give you those intensities. That means how much carbon, how much, you can get a rough estimation based on the peaks. How high are the peaks, right? And then you can get, and that is precisely what is done with uh, X-ray diffraction, all right? So you basically get to know the material, and you also know what is the crystal structure. Right, like I told you, zinc oxide has two different crystal structures. I mean, it can either be in like a Wurtzite structure, or it can also come as a zinc blende structure, depending upon how you make it. So your X-ray XRD will tell that this is a Wurtzite structure, right? So I'll show you how all these are done if I get enough time. But so X-rays we can use as probes for all these measurements, and that's why X-rays we do not hardly talk about imaging except in medicine and surgeries and medical. We normally talk about spectroscopy. All right, so X-ray diffraction is also a spectroscopy technique, and X-ray photoelectron spectroscopy is also a spectroscopy technique. All right, that is called XPS. So we will generate some waveforms, we generate some graphs, plots, but not images using X-rays. Okay, The main problem with imaging with X-rays is that the intensity is very, very low because we are talking about signals that are released by electrons within the atom. The energy is very, very low. And that's why we really need to increase the energy to a very, very strong, also, high intensity we have to generate. And that's why it's a very expensive process. All right. And that's why we don't really use X-rays unless we really want to go specific to the element because that is unique. That's the best way of knowing, right? Now, we can use neutrons also for neutron diffraction. Not a very easy process because neutron is at the core, right? You know that a typical atom has protons and neutrons at the core, and electrons are moving around. So it's very easy to remove electrons and use the electrons for certain activities. But getting a neutron out is not so easy, but it is done, right? Okay, now I am using the term diffraction. Nobody is asking me what is diffraction. I guess you know what is diffraction. See, that is very, very, very important that you keep on understanding the terms being used. Otherwise, you will be lost. All right, now one question which everybody asks and is very common question. You should know the answer because this is a school level question. Okay, I want one answer from somebody, please. The question is, why is the sky blue? When you look at the sky from the earth, why do you see it blue? If you go up and see, you won't see blue. So where is this blue color coming from? Can somebody tell me? Why is the sky blue?
C. It comes from C.
It comes from sea.
Sir. Yes, sir.
That means you are saying it's a reflection of the color of the sea. But what is
Yes,
the
sir.
sea?
Yes, sir.
Sea is water, right?
Yes,
Yes or no? So sea is water. So why is the water blue?
yes,
I mean, you bring some water from the sea, go to the middle of the sea, which is dark blue color. You pick it up in a glass and look at it. Will you see blue color? You won't. In the glass, it will appear transparent. Okay.
due to certain wavelength.
Sorry.
Due to wavelength.
See, it is all about some physical phenomenon happening with light. Right?
Just scattering, right?
Scattering. Okay. Okay. So what is scattering of light?
Sir, the light that straight passes on straight path and get deviated.
Okay. Okay. You're getting close to it. Okay. Okay. Fine. So this is related to scattering of light. Okay. Uh, the first person who thought about the sky, no, the sea being blue. Why is the sea blue? That question first came into mind of an Indian scientist. You know who is that scientist? Sir C.V. Raman. He was traveling to London, and at that time people
Yes,
travel
sir.
by ship. And he was standing on the deck and looking around and thinking, why is the sky ocean blue at parts? Why is it green at parts? Why is so many different colors coming in? Uh, well, honestly, for the ocean to be blue or the sky or the sea to be blue, it is not really diffraction. That's a totally different phenomenon coming in, which actually finally related to what we call as Raman scattering. All right, so it is a different type of scattering, uh, unlike what is scattering happening in the sky. All right, so scattering in the sky is more because of diffraction. That means, there are a lot of small particles that are suspended in the atmosphere. Okay, and when white light grazes, grazing means just passing over very minute surfaces, tips, like you can say tips. So these particles are so small. As light grazes, then what happens? Those waves of light that graze, right? During the grazing, what happens is that scattering happens, and scattering basically means that the individual components. You know, like we say, white light is a composite mixture of photons from 400 to 700 that we see, and the other photons are also there. So what happens? All these different wavelengths, they get deviated in different amounts. Okay, they get deviated. That means as it scratches over, light changes its direction, and the whole white light does not change the exact amount in the direction. That means red light will change to a particular angle, blue light will change to a particular angle, green light will change to a particular angle, and all of them spread out. That means it's like using a prism. If you use a prism, you can break white light into its components. You've seen that, like in a physics lab, right? So you see all the individual components, the different colors. So same thing happens here. And blue light, okay, blue light and red light, which one will have a bigger wavelength? Can somebody tell me? Which one has a bigger wavelength, blue or red? Someone? Come on, we're just talking about it, right? Give Geo. Violet,
Yeah.
indigo, blue, right?
All right.
Yeah. Blue will have a what? Higher wavelength or lower wavelength?
Lower.
Lower
Lower.
wavelength. Lower wavelength, exactly. The
Red
moment we
is
are
higher.
saying lower wavelength, if you relate that to energy, you know what is the energy formula? Where is my, yeah. If we talk about energy of a wave, this is given by h nu. Nu is actually the frequency, or you can even write hf, right? So h is a Planck's constant. So it's a constant value, but we are talking about f. So f we can say is c by lambda from the previous equation we had put in here. So it is E is equal to h c by lambda. So the moment when we say that lambda is less, means as lambda increases, obviously energy will decrease, right? Energy will decrease because it is a reciprocal. That means if lambda is small, energy is high. If lambda is high, energy is less. That means blue light has a much higher energy as compared to red light, right? Because blue light has a lower wavelength, its bottom, that means higher energy. And that's precisely, since the distance is so large, the waves with a higher frequency will travel higher distance and at a faster speed. That's why blue light being prominent as compared to red light or yellow light, we see blue more. Okay, and that's why the sky appears blue. All right, but of course, there are other issues also. Like if you look at time just before sunset, when the sun has traveled towards the horizon, you will see it's mostly reddish in color. The sky becomes reddish. Now that's again for you to find out why is the sky reddish during evening. All right. So anyway, that is something you have to think about. Now we can use ions also as a primary probe. An ion, I already explained to you before, it is an atom which is charged. Okay, a charged atom is an ion. So how do you charge an atom? By removing or adding electrons. Okay, it's always easier to remove than to add, because mostly the available states are already being used up by the electrons there. Okay, so say suppose as an example you talk about carbon, which is atomic number 6. What does that mean? There are 6 protons there, 6 neutrons there, 6 electrons there in the atom. So if those 6 electrons are already there, how can you plug in another electron? Right? but it's always easier to pull out an electron. You can do that. The moment you pull out an electron, you can try to add up a positive charge to it, right? Now, one unit of negative charge on an electron. Okay, so you know how much is the charge on an electron? What is one unit of atomic charge? We call it. Any idea? 1.6 into 10 to the power of minus 19 coulomb. That is the charge on an electron, and we call as 1 unit charge. Okay, so one electron gone, one net positive unit charge added up to the atom, right? And it becomes an ion. You pull out 2 electrons, it becomes an even stronger ion. Pull out 3 electrons, it becomes an even more stronger ion. Okay, so there are a lot of advantages of having charged atoms. The ions are charged atoms. Okay, so they are normally, used for a type of spectrometry which is called secondary ion mass spectrometry, and it is also used for cleaning surfaces. That means ions are bombarded, and ions have some energy in the form of a momentum, because you see, if I strike something with electrons, the physical effect, that means hitting and removing something, is much less with electrons, because the electronic mass is very, very less as compared to an atom, because the mass of an atom is at the center, at the nucleus, right? And an electron is a separate entity altogether. So electrons hardly contribute to the mass of an atom. It is the protons and the neutrons, right? That's why if you have a complete atom coming and striking a surface, it will have a lot more momentum, because the mass is high, and your momentum, is mass into velocity. So if you're striking a surface with the same velocity by an electron and an atom, the atom will do more damage. More damage in the sense that it can actually clean up whatever is lying there. It can actually impact them and throw them out. Okay, that's for cleaning surfaces. We normally put the sample in an ion chamber, and we bombard some ions on the surface, and we get a cleaner surface. Okay, so cleaning is used, and thinning is another process. That means we strike out material from the top by hitting with the ions, and we can make the sample thin also. So I had really worked intensely with this a process called ion implantation. So basically make some ions and we forcefully put them on a surface, and I had to use ions for various applications. Sometimes if I get time, I'll discuss. Okay, so I was working with gallium ions. Okay, and gallium has a huge mass. Okay, many atoms, many protons and neutrons at the nucleus. So it's very heavy, about 80. So it's very heavy. So that's why we use gallium ions there. And this can be used to cut out materials, right? Now, anyway, we are talking more of imaging now, so I won't waste time on the ions. Now come to the electron. Now that is very, very attractive for us. So where do we use electron as probes? In scanning electron microscopy. Then in transmission electron microscopy. These are two different types of microscopy. Electron holography, right? I hope you know what is holography. All right. Basically, we can actually generate images by allowing the light or electron to pass through a number of lenses, and we can actually generate a real 3D image of the what we are trying to look at. Then there's a process called EELS. Okay, we have another 5 minutes to finish up, but at least let's discuss this slide. So there is a process called EELS. Okay, electron energy loss spectroscopy. So here also is a spectroscopic technique. That means we are getting some signals as output, all right, and we try to extract information from the signal. So basically, what was this? We pump in energy to the electrons, and then we see how the electrons lose that energy. Okay, so and then we plot those losses. Okay, how the energy has been lost, what is the change in what is the variation in the loss of the energy, and we call it EELS, electron energy loss spectroscopy. Eel is a fish, the name of a fish, right? So I remember when I was working in Sweden, we were working a lot with eels. Okay, a couple of our PhD students were working with eels, and we wanted to have an international conference on eels. And my boss told me, you may make come up with a beautiful you know logo type of a thing, for this particular uh, conference. And I put in a eel fish there when I did it. Okay, I made a few variations, and in one I put a fish. And my boss there, he's a German guy. He went crazy. Oh, what is a fish doing in an electron microscopy and electron imaging conference? I say it's not any fish, it's an eel. Okay, so anyway, that's off the track. But we did work with eels. Then energy dispersive X-ray spectroscopy, or EDS. Now EDS is a technique that is used for elemental analysis. I already talked about it a little while ago, that since X-rays are unique to elements, we can graze an X-ray over a sample and get to know what different elements are there, what is the material made of, right? So that is actually done in the process called EDS. Sometimes it is also called EDX because it uses X-ray. So both the terms are used, EDS or EDX. And then we talk about Auger electron spectroscopy. Now that's another technique of gathering information from a material using what are called as Auger electrons. Okay, now there's another type of electron. Now type means, I'm not talking about the shape or size or something. All those electrons are electrons. Okay, type means where these electrons are generated. And so Auger electron is a type of electron. I don't have time today, but I'll definitely explain to you what are Auger electrons and how X-rays are formed also. So Auger electrons basically are some electrons that move inside the atom from different energy levels, and they also are very unique, and they provide a lot of information, but very difficult to find because Auger electrons, formation of Auger electrons is very, very limited. So if you're somehow pulling out 1 million electrons from a particular material to study them, maybe hardly 10 or 20 of those 1 million electrons will be Auger electrons. Sometimes it may be more also, okay, but very difficult to take. But once we can detect those Auger electrons, we can actually gather a lot of information about that material. So what I was talking about in this slide is all those different probes that can be used to gather information from a sample which is not visible to us. So it's not only the shape or how it looks like, it will also give you a lot of information about the type of crystal it has, how the atoms are oriented, what is the spacing between the atoms, right? What materials are present, all of those. Like here, we have shown about two different types of electron microscopy. One is called a scanning electron microscopy, and the other one is a transmission electron microscopy. Okay, so what is the difference? In scanning electron microscopy, we actually see exactly like a digital camera has taken a picture, a photograph. A typical digital camera, optical digital camera, you see everything in a sort of a three-dimensional effect you can gather from it. Right? So in scanning electron microscopy, you can take images of a surface of a material. You put the material in, you want to see how it looks like. Say you put a substrate on that, you put some nanomaterials that you made,